Okay. I think we're live. Have to make sure though. See what YouTube says. Yep, that seems to work. Very cool. Right. So this is going to be very small. Okay, I have to definitely increase the size of the text here. Okay, I wonder. Maybe I should just project onto a smaller screen. Yeah, let's do that real quick before I get into the actual programming. Okay. Is that better? Kind of. Now I have to fix this. Oh, geez. Oh, geez. There we go. That's better. Right. Let me just get my project up here. BMJAP. My audio programming adventures. Let's call it that. So, I've always had a real curiosity in how audio programming is done, how applications like Logic and Pro Tools and Ableton manage to process audio in real time, and how all of these effects work, and really exactly what the technology is that they use behind it. And I wanted to go in and, with as few libraries as possible, start building actual stuff in C++ that does real-time audio processing, to basically see like what kind of things are happening all the time when your computer is processing audio, because a lot of stuff is happening to make it as performant as it is. Like, you don't realize how you may not, if you're not deep into this, realize how challenging it is to be taking in audio data in real time, processing it in like a fraction of a few milliseconds, just a fraction of a second, a few milliseconds, to then send it back out to a stereo for people to hear and have virtually no latency. So one thing I want to do first is set up a programming environment in C++ with a few libraries so that I can do some interesting things. And then once I've set that up, I want to go and start implementing some audio effects. Like, one of the things I eventually want to get to is building an EQ programmatically, like an equalizer with a high cut, with a low cut, with high shelf, low shelf, band passes, with the Q knob where you can get different ranges of band passes. I want to go and implement a full EQ. That's like the first thing I want to try and do. I'm not completely sure to whom this would be applied. This series would be good for, because you need to be quite a programmer, quite like fairly good at programming, or at least interested in programming. But at the very same time, you have to have an interest in audio and audio processing. So if you are good at programming but not that good at like, or not that into music making and producing, then I might be mentioning lots of terminology that's common in production circles that's not common in audio programming or in programming circles. So for those listening live, remind me when I say shit that doesn't make sense, that needs to be explained. And the same for the opposite, where you might be a musician or a producer interested in computer science and what happens under the hood in Audacity or Ableton or you name it. I might be glossing over things that are crucial to understanding it that you want to see. So without further ado, I'll get right into it, which in this case, like, the first thing I need to do is set up an environment where I can make an actual program. And I've prepared something here. What I've prepared is a repository that I've called BMJAP. It's on GitHub, it's public, so you can clone this yourself and start work on it. Actually, to show that I could, well, I've cloned it in here. It's just a pretty much blank slate. I'm going to explain to you what I've got in here. So when you're working in C++ as a compiled language, there are many ways to compile it, and the compilation process can be quite complicated and varied. If you're working all from within Xcode, then everything might be taken care of you by Xcode, but then it's not portable. Then the only place you can compile it is in Xcode on Mac. If you're working in Visual Studio, you might face similar issues. So I'm going to be using CMake, which is a simple way to build your project on multiple platforms. So in this case, I have a CMake. I'm setting, so CMake just put CMake lists files in your repository that explains how to build the project. And what I can do, because I work in Xcode, I can then go in here and make, so let me just clear this. Right now I'm in my audio programming repository. I can go and say, make a new directory build. It exists already? Okay, well, let's start over. I can make a directory build, and within build I can say CMake, and it will read out all of the files that I have. It will read the CMake files and produce a project. If I do it like this, I'll be able to just make it normally, but I can also say Xcode, which means I can build it for Xcode. So anyone who wants to follow along on Mac, if you have Xcode, all you need to do is install CMake, which you can do with Brew, with Homebrew, and then you can make the whole project, and it will create an Xcode project for you that you can then compile it with and debug it with. So right now it's reading through all of those files and creating the Xcode project, which I can now open, which should be called that. Yeah. Okay, let's see if this works. I'm just selecting to build just BMJ app. There's a few other things that automatically get added because of the libraries I'm using. But let me just take you through everything that I'm using to get this project to work, because it's actually quite, it's as bare bones as I was willing to make it. Okay, here we go. BMJ's audio programming. One window with Hello World written in it. Okay, so this is one thing that I find very important when doing any kind of project. I prefer to actually make something graphical instead of just working from the terminal. If you're doing audio processing, you could just do the audio processing part and have no user interaction. But I think it's much more fun if you do allow user interaction and something graphical. So what I've got here is this program is using a library called DDUI, which I'm working on, which is a wrapper around NanoVG, which let me show you NanoVG. I realize I'm saying so many things. I'm throwing lots of different stuff at you. But essentially, if you want to create a graphical user interface that's native, that's built in C++, there are many ways to go about that. And one of them, which is like a more low-level approach, is to use openGL. OpenGL, you can just draw stuff with the GPU. And there's this nice library called NanoVG written in C that allows you to do vector graphics. So it comes with the ability to render text. It comes with the ability to render images, and it's got this entire library dedicated to creating user interfaces. So that's what I'm using. And I've been using this for quite a while on my own projects. And so I've decided, why not use it on this? Why not do some audio programming using NanoVG? Okay, I'm just going to start coding instead of talking too much. The first thing I wanted to do on my list is loading and decoding an audio file from disk. When it comes to audio programming, let's see, it says my stream health is very bad. I wonder if it will recover. Maybe I'll just wait for it to recover. Okay, the stream has resumed. Hopefully it'll stay that way. So, when it comes to audio processing, there's a lot of things involved. First, you have audio files that are stored on disk, like MP3s, AIF, WAV files, OGG files. These are all different formats for storing audio on disk. And when you're doing any kind of audio processing, it can be useful to be able to load audio files from disk to then play. So that's what we're going to be doing first, is actually loading and decoding a bit of audio to then play as a next step to stream to the speakers. So let me show you the main file here. This is what I've got so far. So if we compare that to the application that we've got running, that's what it says, hello world. And this is the source code for it. Let me just put that in the corner. So what we have is we have a main function. And so in the main function, we're making one call, DDUI app init, initiate the application. DDUI manages the graphics and the UI system, and underneath it uses NanoVG to allow you to render stuff. And this first call sets up our window. So we're saying it has to be 700 wide, 300 tall. It has to have this as the title, BMJ's audio programming, which it has. And then we have to give it a function called the update function. And the update function will be called whenever DDUI wants to render a new frame, completely re-render the view. So it's actually the simplest form of GUI programming you could have, where you just redraw, just like a video game would, you redraw the entire UI on every single change. And I've built really seriously complicated and sophisticated interfaces just using this technique, and so have many game developers, and there are many examples of user interfaces that are built this way. And I think it's a really fun way of programming or building user interfaces. So for now, there's no audio processing stuff in this entire application. We just have DDUI being initiated. Provided it doesn't fail, we then create fonts and we run the app. Creating a font is actually something that you do in NanoVG. The way that works is, if I bring up the documentation for this, and all the documentation for NanoVG, I believe, is just in one header. Let's look at this. Okay, nanovg.h. NVG create font. Okay, so when you set up NanoVG, you can take a file name to a TTF file, true type font format file, and you can give it a name that you can refer to it from within your application. It will load in that font, and it will take care of all the rendering of the font. You just say which font you want to use, and then you can render text. So we can see in the update function how I'm using this. So I've registered a couple fonts here. A regular font, which uses San Francisco regular, a medium, which uses San Francisco medium, bold, thin, and a mono font, which is for PT mono, which is a monospace like scripting font. In the update, I select the font face regular. I select a font size 48, a fill color, and this is like the hex code for the color. So red 0, green 0, blue 0. We set a text align to be centered on the horizontal and centered on the vertical in the middle there. And then we draw text, and that's just with DDUI text. We say we get whatever the viewport is, whatever we can see, we get exactly half of that to get the center point and the center point of the height, and we draw hello world. So let's start. Let's for the time being ignore this GUI code and load up a audio file. Loading up audio files is kind of complicated because of how encodings of files are maintained. MP3 is actually restricted in who's allowed to use it. There are no, like, I don't think there are any open source. I'm not sure, but if you wanted to read MP3, the best thing you do is use the operating system to load it for you. Because in the case of Apple, they have Core Audio, which has helper functions to load from disk MP3, AIF, M4A, all sorts of different audio formats. So if you want to do that, if you wanted to load all sorts of different types, you could use the operating system. Or you can use something called FFmpeg, which is a open source encoding and decoding and basically audio video processing library, which understands all the different encoding formats. But that's a big library. So what I'm going with is, for now, just supporting OGG. What is OGG? OGG is free open container format maintained by Ziff Foundation, whatever that is. This format is another file format similar to MP3 that is open source, and the nicest thing about it is you have this this guy called STB. What would it be? STB Vorbis? Yeah. You have this guy STB, which stands, I think, for Sean something. What is it? Sean Barrett. Sean T. Barrett, who wrote a single file which you can include in your project that will be able to load OGG files, OGG Vorbis files. So we're going to be using that. I'm just going to get the raw file here and just paste that into my project. Okay, it's a lot of lines. So to then include it in my project, I have to do, let's see. Do I want to write this as a header file, or do I want to write this as an implementation? Not quite sure right now. Okay. That's a curious one. If I want to use this as a header, getting a bit stuck here. Nothings. Okay. What's the right way to include it? I forgot. Well, you know, DDUI uses STB image. So maybe if I just see how does NanoVG do this? It has STB image. You just define implementation. Okay, cool. maybe that was right at the top of the file and in STB image, in STB Vorbis as well. No. Okay, so we want to use this in our project. We have to include it. Define that and then include what would be STB Vorbis. See, I just don't understand with Vorbis. That's kind of weird. Why is Vorbis a .c as opposed to a .h? All of the other ones are .h. See how weird that is? Maybe what I'll do is define that and then include stb vorbis .c. I have to add it as a source file, of course. I'm a bit lost here. Yeah, that's not what I wanted. Okay, so when you include this, it will include all of STB. So I do not need to write STB as this. I don't even want to start to explain all of this stuff, because there's such a, to me, in my mind, there's such a stupidity with the way C++ compilation works, where you have these compilation units and you have header files, and it's that one thing that you just want to get out of the way so that you can then just continue programming normally. It sucks. Absolutely sucks. But okay, our program is compiling with STB Vorbis. Now, how do we use STB Vorbis? So there should be like a pretty straightforward file for loading a single audio file. So we've got a few things like stb decode file name. That's the one. So they call it stb. Oh geez, what has happened? stb decode file name. That's the one we care about. So in main, after we've loaded up our typefaces, let's load our audio file. And we want to use stb vorbis decode file name. It will return an integer, which I believe will be the number of samples, but that's just my guess. I'm going to decode it, so we have to give a file name, and then yeah, we want to have int num channels, number of channels, sample rate, and then a pointer to shorts output. So the file name for now, do I have an OGG file that I can, I believe I have one here, assets, no, not there. Assets for the project, I have this one called roads.org. Let me just show you what that sounds like in Audacity, I imagine. This is what we have. Very simple. Just some Rhodes melody, stereo channel. So that's what we're going to work with. This is encoded as an OGG file. And this first function that we're calling is going to turn it into, supposedly, a give us the raw samples. I just want to quit this. No. Okay, Audacity is just stupid. Why has everything broken? I just close a file that I haven't edited and it just crashes. Okay, great. So the location of that file is, I have assets here. In DDUI, I've added some utility methods for locating where assets are once they're compiled and put into the project. So I'm going to rely on that. Where do I find those? Include DDUI. Get asset file name. So I have to go here. DDUI get util get asset file name. So I'll show you that before I do any stuff with STB. I'm just going to do DDUI. Is that how it works? Let me just switch to Xcode for this. Get asset file name. And we give, what was it called? Rhodes.org, I believe. And we get back some kind of string. So if we just print that, we should get the file name. So this is where it's stored. Users, BMJ, library, mobile documents, blah, blah, blah. So it's in iCloud. Projects, audio, programming, build, debug, BMJ app.app, contents, resources, assets, Rhodes.org. That's the full file name of where our asset will end up. How does this work? So in the source tree, in the root, we have source where I have all my code, and we have a folder of assets where I have all my different assets, including Rhodes.org, like a metronome sound that I might use later, and all my fonts. And in my main CMake list, I define all of those as assets that I want to use. So all of my fonts and then my org files. And then what I do is, when building for Mac, I tell the Mac to include those as source files. And what else do I do? Add executable, I create a Mac bundle with my source files and my assets. And so it will make sure that they end up in the right place. Oh, here. So here I set the properties. All those assets should be stored in resources assets. And so when Xcode compiles it, it will make sure that that gets copied over into the bundle. And then DDUI will give us the right file name for that, which is exactly what we want. Yeah. Okay, so now that we've got the right file name, we can call that file name. Then I can do I can actually get my file name. I can give it my channels and my sample rate and my output. And hopefully STB Vorbis will do the right thing. We can check. So afterwards what we'll do is we'll print num samples. We'll print out all of the things it should have returned. So num samples, num channels, and sample rate. I'm going to leave out the output itself for now and see what happens. Build failed. What did I do wrong? Oh, yeah, this is called num channels. Okay, cool. Num samples. We've got 769,000 samples, 2 channels at a sample rate of 44.1K. Okay. The way audio is stored is as samples. I guess it's worth opening Audacity again if it will not crash this time. We can go through and see what it's doing. So roads.org, this is what gets loaded. And when you zoom in, let's zoom into like this point here. At the micro level, we have these here. That's a single sample, that thing right there. And let's see if I can zoom in anymore. Yeah, perfect. So they're just measurements of the pressure of air at the point of the microphone, or whether it's synthesized, whatever. And when you turn these into an analog signal and you send them to a speaker, the speaker will vibrate and reproduce the sound that you've recorded, hopefully fairly accurately. And when it says we've got 700,000 samples, it means all of these little points. And the sample rate of 44.1 kilohertz means for every second of audio, we'll have 44.1 thousand reference points or little measurements. And it's stereo, so we have 2 of these. We have 2 channels. So what can we do with this? Can we stream it to the output? Yes, let's try and do that. So now we're getting into the terrain of audio outputs or audio streams. The way that works in all computers conventionally is you have a buffer, and the buffer is usually a very short interval of time, let's say 64 milliseconds. And what the operating system does is when it sees that you're an audio application producing audio that has to go to the speakers, every 64 milliseconds, it will ask you, okay, you need to give me 64 milliseconds of sound. And you have to then give it to the operating system as fast as possible. Once you give it to the operating system, it will play those 64 milliseconds of sound out to the speaker. And whilst it's playing those ones that you gave it, it will ask you for the next ones. And every time it runs out of those 64 millisecond chunks of audio, you have to back it up with another buffer and continue on that length. And continue doing that without any interruptions. If you take too long calculating the audio and you go over those 60, you get past your time frame, then the user will hear it, because there will be no buffer. There will be emptiness for 64 milliseconds. And even like an emptiness of even if your buffer is like 16 milliseconds, you'll be able to hear the emptiness as like a crackle, because you have this wave that's normal and continuous that suddenly grinds to a halt, goes to 0, and then starts up again. So that's known. That's really obvious to hear. I mean, so when we're doing audio processing, we always have to think of it in terms of how to process the next buffer, and we have to think of it in terms of getting that buffer out as quickly as possible with as little delay as possible, so that it will appear as continuous sound to the user, even though you're actually processing it in these chunks. So yeah, let's get started with that. So what I wrote up before starting is this thing that I call audioclient.cpp, and it's roughly based off the example given for this library called libsoundio. Oh, was my stream interrupted for a bit? That sucks. Let me go back and see how much I missed. I don't know. Okay, whatever. Okay, libsoundio allows you to communicate in a cross-platform way with the operating system to set in motion this dynamic of filling buffers. because there are many drivers that do this thing. In Mac, it's Core Audio that does all of this, but you also have ASIO, you have ALSA, Advanced Linux Sound Engine or Sound Application, I don't know, whatever it is. And so all of these different ways, and Windows surely will have other ones. You have Jack, many different clients, many different ways of processing audio. SoundIO abstracts away the individual differences of these clients. So if we go to libsoundio, here we go. C library providing cross-platform audio input and output. So it supports different backends. It supports Jack, Pulse Audio, ALSA, Core Audio, WAS API, Windows Audio API, I assume, and enough like silence. So this is what we're going to use to get our handle, our ability to fill audio buffers. And because it's all in C, what I've actually done is kind of written a wrapper that abstracts away a lot of the things that I don't use, because SoundIO allows you to do everything. It allows you to scan for the different audio interfaces or devices connected to the computer, to pick one, to change the sample rate to a desired amount, change the buffer size to a desired amount, and to like connect to multiple devices simultaneously. It allows you to do a lot of stuff, and really all I want to do is just connect to the primary audio interface and to get input and output streaming, and that's all I want to do. And so what that boils down to is one function that I wrote here. I'll open it in here actually, which I've called init audio client. I give it the sample rate I want, and I give a read callback and a write callback, which will be for reading data from inputs like microphones and writing data to headphones and speakers. So what is a read and a write callback? What they look like? They are as follows. They're a function that returns nothing, that will take a num of samples, which is like an expectation of this is how many samples you have to fill in this buffer. A number of areas, which is synonymous in this scenario with the number of channels to fill. So if you've got, in the case of a write callback, usually you have to fill 2 channels to fill stereo audio. I'm connected up to my Focusrite audio interface, so I actually have what would be 6 outputs that I can send to my Focusrite. And then for the read callback, it's effectively the same thing, but here you get these buffers and you can read from them instead of filling buffers. And in the case of my Focusrite, that would be 18 different inputs. And to initiate the audio client, you just give a read callback and a write callback. So let's do that. So in main, we've loaded our file here. And what I then want to do is initiate my audio callback. So I'm going to do init. I'm going to actually include it first. And then we're going to do init audio client. I just want to go with that same, just go with the same sample rate of the file, the one that the file has. Need to put in a failsafe here of if num samples is less than or equal to 0, printf failed to load our roads.org file, and just exit like so. Then what we'll do is we'll initiate the audio client at the sample rate of the file we opened, and we have to give a read callback, but we don't want to read anything from the microphones at the moment, so I'll just give it an empty. I'll write one. I'll make a read callback. Okay. Areas. Okay, what we've got is, I don't want to do anything in the read callback. I don't care what the microphone inputs are at the moment. I only care about the write callback. So now that it's been opened, oh wait, first of all, init audio client, I have to finish this. I have to give it my read callback, my write callback, and that should be everything that I need to do to set up my audio client. So let's see if that compiles and runs. It works, but it's going to be passing us a buffer which is likely uninitialized. It will have random shit in it. And if we don't put our own shit in these buffers, it will just send this noise straight into the speakers. And it will sound like a tone because it's not exactly noise, because it will just have one, it will give you the same buffer each time. It's not reallocating memory. So if you don't fill that buffer the first time, it'll be random. And the second time, it will be the exact same randomness. So you have this repeating randomness that just gets sent out straight to the speakers. And it sounds like shit. So the first thing we want to do is fill everything with zeros. I'm going to look at my area here. So area is a little struct that I've got. It's quite messy because it's got lots of different functions. But essentially, it's just a begin pointer and an end pointer that sets out it's essentially a beginning pointer and an end pointer that sets out a region of memory that contains or should contain audio samples. So in the case of the write buffer, this is where we end up putting stuff. And we have this operator here that allows us to, when you dereference it, you can set the value of the pointer. So what we can do here is, this is kind of where it gets really simple. How do we want to do this? While our areas, we're going to do for n is less than number of areas. Well, we're going to have an area. And we're going to say while, maybe I'll just call this pointer. Well, area. While the area is less than area.end, we're going to say write the value 0, the floating point value 0, into that area and increment the pointer. So that we fill in a 0 in one of the samples, jump to the next one, fill in a 0 there, jump to the next one, fill in a 0 there, until we get to the end of the file, the end of the buffer, and then we're done. And the ending is encoded in this .end variable. So each area will have a beginning and an end and a step, which means that for every point that you write to, you might want to skip a few points because of the way it's actually stored in memory, which is taken care for by that plus plus, because the plus plus increments our pointer by a step. If you're not a fan of object-oriented stuff, neither am I, but I'm using it in this instance because it does really clean up the code of processing these numbers, processing these arrays of floating points. Anyway, that should have done it. For every area, we will be filling in zeros, so it should be silent. Good. Okay, we've got silence. Let's now actually start writing our file in. One of the issues, though, is that the file, once it's decoded by STB, is in the format of a signed short, an integer. We have to convert this to a floating point. which is not so bad. Well, the first thing we want to do is just allocate. Maybe we'll make a little function for this. No, we'll just write it inline. So float pointer, float version, output converted. We want to get, we have 2 channels. Actually, we can just do it like that. We have to allocate an array large enough to store all samples, and then we just need to convert. So what I can also then say is short pointer output pointer. It's the output there, and then output pointer end, which should be output plus num samples times num channels. We should never cross over that pointer. So this is basically an iterator. So we can say whilst our output pointer is less, our output pointer end. Yeah, I don't like the naming here. What I'll change this to is avoid convert short to float, convert samples. Convert samples, taking in an integer num samples and input and output array. So all of this, what I want to do there is I'll call this input output converted convert samples. Our number of samples, I'll multiply up the samples and channels so that we just have one array. We don't care about whether it's stereo. We just know that it's one contiguous chunk of samples. That's all this function needs to know. We'll give our input array and our output array, and we want this to fill the input with the output. Let's paste that back here. Now this should be in pointer end, for as long as in pointer is smaller than in pointer end, we're going to do a conversion and put that in our out pointer, which I'll call float out pointer. So effectively we need to do something like this. Out pointer plus plus will equal to some kind of conversion of in pointer plus plus. And what that conversion is, we'll do a little, oh yeah. We'll have to do something like inline float convert sample, float pointer, no, short sample. So when you've got a sample stored as a integer, the maximum value of the wave will be whatever is the max short size, which I guess would be 2 times 2 to the power of 16. Is that? They have constants for this, but I don't want to look it up right now. That's the maximum. No. 15. Because it's signed. It has one signed bit. The maximum would be that, and the minimum would be that. Ranges between those two values. So first thing we want to do is perhaps just turn it into a double, and then once it's a double, how do you do it with, do we ever use minus? I guess I'll just divide it by, again, I got it wrong, it's 32. Divide by that as a double. Wait, that's unnecessary. Divided by that. That now it's between 1 and minus 1. And all we need to do afterwards then is just turn it into a float and return it. And that's our conversion. Maybe. So that we have our convert sample. I wonder if convert samples will work. I believe that should be enough to convert it. But the only way to test it would be to play it. How can we play this? Well, in the top here, let's define some static variables. We'll have static int num samples. Actually, no, I'll create static area. What's the constructor for an area? Oh, I can just do null constructor. Static area file left channel. Static area file right channel. There we go. What we want to do here is, so we filled it all with blanks, great. Now we want to fill the stereo channels with stuff from our left and right file. So, okay, what we'll do first is actually create these areas. So once we've converted our samples, we want to store them in these areas. And so how areas work is, yeah, just a pointer where we start and an end. But with an org file, you have one buffer which stores the left and the right. And the way they're stored is you have a left sample, a right sample, and then the next left sample, the next right sample, and so forth. They're interleaved. And so how you can do that is you can say file left channel will equal to an area where the pointer is our output. It starts from our output. We have a number of samples and a step of 2. For every single sample, we make 2 steps to get to the next sample. And for the file right channel, it's just one, it's just like offset by 1. So this one, the file left channel, will always be looking at the even numbered samples, and the file right channel will always be looking at the odd numbered samples because it's offset by 1, and they both always take steps of 2. So that's how we can basically disentangle them. And now all we want to do is just say in our write callback, as long as we still have a sample to write, as long as the file left channel pointer is less than the file left channel end pointer, we've got some material to copy into the areas. Because we know the file left channel and right channel are exactly the same length, we don't need to do it like another condition. We can just write it like this in what it would be. We're going to take area 0. I'm going to say area out left area 0 and out right area 1, which is respectively the left and right channel, the stereo output channels. Oh, areas. So out left dot file left channel. I'm stuck. Okay. Out left. One thing that's important here, I'll rename these in L, will be file left channel. as long as in L is less than in L dot end and out L is less than out L dot end. As long as there's more input buffer to fill and more output buffer to fill, we're going to copy them over. I mean, as long as there's more input buffer available to us and more output buffer to write into, we're going to do that. The only issue here is that we don't remember where to start off. Like, we fill one buffer perfectly, and then we fill this one buffer, and the next time we have to fill the buffer, we're just going to start copying from the same place again. So what we actually want to do is make this have an effect on our static variable, so that the next time we come past, we continue from whatever point we left off at. And so that would mean that we would play through the entire file until we get to the end, and then we stop playing, and it's just zeros. So let's try that. Oh yes. Good. It works. Okay. So from seeing that, we've done a bit of an introduction. We've loaded and decoded an audio file, and we've streamed it to the speakers in a very rudimentary way. Let's render the waveform. But before I do that, I'm going to take a break. But I'm pretty happy with that. It's good that we have audio streaming. There you go. So I'm going to check that in and take a quick break and then start rendering waveforms to the screen so we can see what we're doing. Right. Basic audio playback working. Beautiful. Who needs special screens on OBS when you can whatever. Okay, we're back. And I'm going to get a drink. Okay, so what we have so far is basic playback of the one file that we've loaded from disk. We're not doing anything special at the moment. It just plays back. And once it's finished, it ends. Fine. I want to show that on the screen. So what I'm going to do is make a little reusable component that renders a waveform. So the way I want to do that, I'm going to call this I'm going to make a new directory called views waveform HPP. So what is this going to do? It's going to be a structure actually called waveform. Let's see. It's going to be structure called waveform, and it will have a render function in it. So you create something like that, and you can then call render. So in our main, we're rendering some kind of hello world stuff. We're going to include our waveform. We're going to do waveform render like that. So this is kind of the way I draw my views nowadays. When I create a little structure inline, and I can give information on how to render it. Like I can do dot some option true dot some other option 10 and then render. And so this waveform struct is it's a temporary struct that you build on the stack. It's a temporary struct, you build it on the stack and give it information you want to give it about concerning the rendering, and once you've given all the information, all the options, then you can render it. So we also need to give it some kind of we want to have some kind of waveform state that gets memorized between frames, because we don't want to re-render the waveform. We can render it once and then just put it on the screen on every render. We can prepare it once. So in order to we have to have an image handle, which I imagine will be a void pointer image, or maybe it's an integer. I think it's image. It's an integer image ID, and then we'll have something for now that should be fine. Image ID, and what else? We want to render a single area, like one channel. So it'll have an area pointer. It'll have an area that we want to render. Maybe I'll focus on refactoring this later, and I'll do this, and this will be down here. We're going to say inline waveform render. When constructing the waveform, we want to say give it some kind of waveform state. So as our some private variables waveform state, I can actually just call it state because it's namespaced already. So here This might be a weird, you might think this is a kind of a weird way to write a structure, but it works out very nicely when components become more complicated, that I separate out the state that needs to be maintained between renders of the UI and state that is just temporary for describing what needs to be rendered. So I can put other variables in here that are temporary, that are recreated each time, and the only things I store between renders is stuff that actually needs to be stored between renders, instead of like having entire object hierarchies and relationships. I just don't want to care about that. So for now, that's all. So here we then have image ID. I'm going to set that to -1. Waveform. Here we, so if state.area dot pointer doesn't equal area.pointer, or state.area.end doesn't equal to area.end, area.step doesn't equal to area.step. So if between renders we're suddenly given a new waveform that doesn't conform to the waveform that we've stored before, then we just want to make sure that we set our image ID to -1 so that we re-render. So then during the render here, if we don't have an image ID yet, we have to create a new image. We have to produce a new image and consequently render it, put it on the screen. So I'm going to include DDUI core, and in DDUI core we should have like a create image from RGBA. We have image flags. Do we have the flags anywhere here? Repeat X, repeat Y, pre-multiplied. Nearest, yeah, we don't care about any of those. So there's no flags. So inside here, we're going to say state.image ID will equal to create image from RGBA. The width will be the view width that we get from DDUI, the view height, no flags, and some data. So for the data, we need to allocate a new bit of data. So I'm going to say, what is that? Char? Is that unsigned char or char? Unsigned char. Data, new. Here we want to get, let's see. We want to fill the entire view. So here we can just use W H. This should be W times H times 4 because we have red, green, blue, and alpha. And let's say just for now, instead of actually rendering a waveform, I'm just going to render just a red-filled image. So to do that, we're going to say for int x 0, x is less than width, and for int y 0, y is less than height, we're going to create a red, green, blue. We're going to fill in a red, green, blue, and alpha component. So that'll be x plus the width times y plus 0. Well, for 4 times. That will be the red component. And this will just be zeros, zeros, and then the alpha should be on, so that there's no transparency. And then from that data, we create our image. Once we have our image, we can draw the image. And I think the way we draw the image is we have to create a paint. So paints, image pattern, that's it. DDY image pattern 0, 0, 0, 0. Maybe that's width, height. No angle. Our image ID as the image, and no transparency. And then fill paint or something. DDY fill paint. DDY begin path. DDY rectangle that covers the entire screen. Wait, image pattern, let me just check that. Image pattern, it's floats. Hopefully that should create a completely red image. So let's have some waveform state. And we just render it. We don't give it an actual waveform to render for now. Failed. Oh shit, where did I save the... Where is it? Oh, I put it inside the views. Okay, include views. Huh. In the constructor, I can accept a state there. What's wrong with that? That's correct. First of all, waveform cannot be defined in the result type of a... There we go. Perfect. It renders just a completely red square. But we can change that so that instead of just rendering it right there, it will render it in a subview. So I can say DDUI subview, and we want to render it at an offset of 40, and we only want it to be 300 by 100. And afterwards, we need to restore back to the global view. So after saying this, we cut into a smaller view of the entire UI, and in there we run our waveform. We render our waveform such that, and then we can restore it. Yeah, that's all I need to do. So we get it just there. Cool. How do we now fill that with data regarding our waveform? Well, first we have to give it a waveform to render. So we're going to say waveform. We're going to give it the file static int samples played. We're going to give it the left channel. This is pretty important, that all of these functions return a waveform. So here we have to return so that we can just like pipe them. Here, like a cool thing you can do is, for example, have DDUI color, background color, and foreground color. And we can have, let's call it BG color. Then we can have waveform. Then we say background color. Foreground color, and we can default this to like let's see, that could be red, and blue as a foreground color. We can make these two functions. And here we could this is annoying because here it's written as unsigned chars, but the color object here I believe is floating points. I'm not sure. Yeah, it floats. So we want to actually probably create like an internal representation of colors. Like char BGR BGG. What's a good way to do this? So let's say we pass it a different color, we need to be able to convert to the right color. Yeah. I want to refactor this at some point, but not immediately. So, if I change this, let's see, if I don't define anything here, and our default is a red background and a green foreground, and we use VG color red, green, blue, alpha, green, blue, alpha. If we now go and change in here that we want the background color to be 1, 2, 3, 4, 5, 6. Okay, so it can convert between GDUI's representation of a color to its own representation and then put that into an image and show the image on the screen, which is good for now. I need to change the code here to that plus samples played, and then samples played will equal to in L minus file left channel. Should still work. Shit, it doesn't work. What am I doing wrong here? Oh, this will have to be divided by the step. So we're giving it an area and a background color. Let's give it a foreground color of white at the moment. And now we have to write the code that renders it, which might be a bit tough. Let's see, how do we want to render this? We're going to pass through each vertical axis. We're going to go through horizontally. At any time, for each pixel, we want to get the maximum point and the minimum point of the wave at that point, and render a line or fill in. Yeah, okay, so, okay. we want to make sure that there is actually audio data for us to process. Because if there's no audio data to process, then there's no point drawing something for it. Okay. We create our image. For every horizontal, we need to maximize. So we're here at the first pixel. And we have to convert this to samples of the waveform. So we can see, let's say we want the waveform to fit perfectly into the box, where the last sample is at the end of the box and the first sample is at the beginning. Then sample 0 or I0, let's see, we'll actually write number of samples end minus state.area.pointer divided by state.step as an integer. So those are the number of samples. So like double samples per pixel will be num samples turned into a double divided by pixel, the width. Alright, 0 samples per pixel. Samples per pixel times x turned back into an integer, and then int I1 will be samples per pixel times x plus 1. Okay, so then we want to get max and minimum. I is less than I1. If does the area have an accessor? Let's do an accessor operator. State.area I Okay. Then we should have the maximum and the minimum sample within the current pixel that we're trying to render. With that, we can then do figure out what minimum y we have. So int min y will be whatever is the maximum, which goes, so if the maximum is 1, then min y should be 0. If the maximum is 0, then min y should be half of the height. If the maximum is -1, then min y should be the height totally. So we can get max sample and reverse it, divided by 2. And so if it's a 1, it will now become a -1. It will become minus a half, like so. Minus a half. If it's a 1, it becomes minus a half. We just need to add 0.5, and so it turns into a 0. And if it's a -1, it becomes a 1. Perfect. Then we just have to multiply that by the height and convert it to an integer afterwards. And then we have our max y, which will use the min sample. And so then for our height, as we iterate over the height, we'll have int y 0. While y is less than min y, I'm going to fill in a color. We're going to fill in the background color. And of course, I'll do this as a for loop. Increment the y. Then for as long as it's less than max y, we're going to fill in foreground colors. And then after we've gone past all of those, for as long as it's less than the height, we're going to fill in background colors again. That should be good enough. Size T, what would that be? Standard lib include. Beautiful. We are printing a waveform. Let's get it rendered at a bigger size. So that comes down to here. We want this to be, let's say, 10x the full width minus 20 and a height of 100. Very cool. But as you can see, after we've rendered it once, it won't rescale or resample. The best way to see that actually would be to not have a subview at all, just render it completely and start off with a small window, 100 by 100. And when we scale this up, you can see how pixelated it is. Very pixelated. So what we actually want to do is be able to rescale or re-render it when it gets scaled, because this is really low quality. I have another issue that I realized. If we change the background and foreground color, we need to rebuild the image. So it's actually something that's in long-term state. That if the color changes, we re-render the image. Which is kind of annoying. What I can do is... oh dear. Maybe I don't want to do this right now. What I will do is I will multiply out the width and height here so that I get a retina quality image. That didn't quite work. What I need to do as well is turn this back into like a 500 by 300 window. Okay. Waveform. So we create an image that's bigger in width and height. Then here we have to do width and height like this. Beautiful. You won't see the difference, but that's like retina quality image. Okay, I'm pretty tired now. I'm going to leave it at that. We have the ability to render a waveform, we have the ability to load it from disk, and we have the ability to play it out to speakers, which is a good starting point for a little audio programming framework, a little app where we can play around with stuff. Next time I'll probably come back with a better plan for what I want to do. There are a few things. I really want to start work on what did I say? On doing an EQ. So we're going to start work on building an EQ using some of the things we developed tonight. Great. Cool. I'm going to leave it at that. If you enjoyed this, great. If you didn't, tell me why, and I'll see if I can change it. Have a good night, and I will hopefully see you later. Bye.